Welcome everyone to this class. In today's class, we are going to discuss the problem of multi-port memory binding. Just to recap the high level synthesis steps, so we have already discussed that high level synthesis is a process of converting a C high level behavior written in C into RTL, right, and it consists of several substages like pre-processing, scheduling, allocation binding and then data path control generation. So, we are now actually discussing around this allocation and binding, right, and in the allocation and binding we have already seen that there are two problems. One problem is binding the operation to the function units and binding the variable to the registers or the storage, and we are actually discussing this problem of mapping this variable to the storage. Okay. And in the previous class what we have seen that this mapping this variable to the register is a problem which can be solved either by graph coloring problem of complete graph or click partitioning problem of compatibility graph, right. So, we basically what we have seen that the objective is if there are variables which we identify the lifetimes, and if two variables whose lifetime is non-overlapping, they can share the same register, they can be stored in a same register, right. So, this is what we have seen. But in today's class we try to see this particular problem on a different angle, right. So, earlier what we have seen that the registers are individual entity in the hardware. So, they are actually spreaded over the hardware, and I am going to map the variables to the register with an objective is to use minimum number of registers, right. And what we have seen that if two variable which has non-overlapping access, say they do not have any lifetime overlapping, we can put them into same register, because after the last use of the first variable there is no requirement of the particular variable in the hardware. So, let us remove that and store the new value into that, right. So, that is the overall idea. So, now we are going to see that same problem, the register binding problem, on a different angle, right. So, the angle is something where instead of the register spreaded over the hardware, usually in a system like RISC processor where we have a register bank. Okay. So, bank means basically a sequence of registers stored together. Okay. So, we have register bank instead of individual registers, and the second problem is there that we have a set of registers and they are not going to access individually. Okay. So, what we are going to have? We are going to access through them some port. Okay. So, if you look into the idea is like this. So, we have set of register bank. So, this is my register bank 1, say I have it has say 5-6 registers. There is another bank which is say have say 1, 2, 3, 4 registers, and I am not going to access this register individually. Okay. Rather, I will have a port here, right. So, this is the read combination port. So, if I just put a address here and then if I give a data here and I give a write enable here. So, then the corresponding address where, so suppose this is I have given say register I and this is my register I. So, this data whatever D value and will be stored in this particular location. Okay. And similarly, if this write enable signal is 0, that means I am going to read it. So, this data does not matter here. So, I am going to access this register and that particular output will come here, right. So, this is what is the port, and similarly this is the port combination. So, port combination 2, right. So, now what is the problem? In the hardware we have set of such register bank, okay, and I want to map. So, this the number of port may be flexible, but usually it is 1 or 2 in the hardware, right. So, this is my register bank 1, this is my register bank 2 and so on. So, there are such combinations. So, there may be say 10 register bank, each consists of 10 registers. So, there are say 100 registers are available, but it is not that I am going to have they are available individually. Here the problem is I have set of variables, I have to map them to registers, but here their access is restricted by the register bank and their port. So, we have to map this variable to the register bank. Okay. So, that is the problem. So, that this is what is the memory binding problem, right. So, basically it has a multiple port and it is a memory, right. So, set of a sequence of register is basically a memory. So, now we are mapping these registers this variable. So, this is actually variable. So, variables, I am mapping these variables to the memory which has multiple ports, right. The number of port is also limited. But what is the problem here? Why the solution that we have discussed in the previous class, that you do a graph coloring or click covering, why that particular type of solutions will not work here? Okay, let us try to understand. So, let us take the same example that I have taken earlier. So, this is my schedule graph, right, and I am actually try to map this variable Z1, Z2, Z3, Z4, Z5 and Z6, right. These are the 6 registers I try to map. So, in my earlier, when my registers are actually spreaded over the hardware, what we have seen that we actually identify the lifetime, right. So, we identify the Z1 lifetime is this, Z2 lifetime is this, Z3 lifetime is this, Z4 lifetime is this, and this is the Z5 and Z6 lifetime, right. And then what we have seen that since this Z1 and Z2 is overlapping, Z3 and Z4 is overlapping, and Z5 and Z6 is overlapping. This is the conflict graph, right. And the conflict graph, if we try to put the color, so I can put color 1 to this combination and I can put the color 2 to this combination. So, this is my register 1 or color 1, this is color 2 or register 2, and this is perfect because this Z1, Z3 and Z5 they are actually have a non overlapping lifetime. So, the single register can store this. Okay. Now, come back to this multi bank register bank, right. So, let us just say I have a one register bank which has say 5 registers, right, and it has 2 port. Okay. Let's have a 2 port. So, what we have seen that this Z1 and Z2 cannot share a single register, right. That is what we have seen because they are actually accessing the same time step, right. But now, if you think about the register bank, since it has 2 port, I can put both Z1 and Z2 into the same register bank, not into the same register, but in the same register bank, right. Why? Because it has 2 port, and in say one in the time step 2, since I have to access this Z1 and Z2 and it has 2 port, I will read Z1 through this port and Z2 through this port. So, so obviously they are not mapped to the same register. You try to keep in mind that they are not mapping to the same register, but register bank, and bank is set of registers. So, they will be placed into different register, but these 2 variable can be mapped to same register bank. Now, if you assume that I have already mapped this Z1 and Z to this, Z3 cannot be mapped to this. Why? Because in this time step what operation I am doing, Z3 equal to Z1 plus Z2. In this time step what operation I am doing? I am doing Z5 equal to Z3, some operation minus is happening, say some minus constant, right. So, forget about that part. So, then Z6 equal to say Z4 some star something, some input say, right. So, this is input 2 because input are not mapping to register, we are only bothered with the temporary, and here it is happening say out equal to Z5 minus Z6, right. This is what is happening in these operations. So, now what is happening here, Z3, Z1 and Z2, these are the 3 variables that are going to access in timestamp 2, and since I am assuming that I have a memory bank which has 2 access port. So, only 2 of them can be mapped to the same bank. Okay. So, once we say these 2 registers are mapped to the same bank, they will store somewhere, that is automatically decided, right. So, there are series of registers, so you can just put in some places, right. But what is stopping me here, that here Z1 and Z3 was mapping to same register because their lifetime was non overlapping. But here since I have already decided that Z1 and Z2 go to this register bank, I cannot put Z3 here because then I have to access 3 values, right. So, there are 2 read and 1 write, but you have to access that location. So, at the same time, since it has 2 ports, I cannot access 3 values, hence I cannot map both Z3, Z1 and Z2 into the same bank. So, I have to put Z3 in this bank. So, let us say I have another bank of 2 ports, right. So, this is how I solve the first step. In the second step, what I am doing is I am actually I am accessing Z5, Z3, Z6 and Z4, right. Because there are 4 access happening. So, let us assume that in1, in2 is inputs, so I am not considering them now. So, there are 4 access, right. So, I cannot map all these 4 values to same registers, right, because then I cannot access them at the same time. Okay. So, what I have to do, I have to take any 2 and put into one bank, say I am just putting say so here actually Z3 and Z4. So, Z3 is already here. So, I cannot just move it to there, because Z3 already decided to be put here, and Z4 and say let us I have decided to put Z6 here. So, since Z3 and Z6 is already put into this memory bank 2, I cannot put Z5 or Z4, right, because in this time I have to access all 4 registers, 4 values, and only 2 port are available. So, Z3 and Z6 here, and I can put Z5 and Z4 here, right, Z5 and Z4, which is perfectly fine, because this bank stored Z1, Z2, Z5, Z4, but I am only accessing Z5 and Z4. So, 2 port will sufficient, and what is happening in the last step? It is Z5 and Z6, and since Z5 is here and Z6 here, it is actually satisfying the port requirement. I have to access only one value from this memory bank and one value from this register bank, which is supported by 2 ports. Okay. So, this is how we solve the problem. So, you can actually understand that my memory bank 1 will store Z1. You can have multiple solution. I just talked about one possible solution, Z2, Z5 and Z4, and my memory bank 2 will store Z3 and Z6. This is what is the solution I got. So, you understand that here the problem is not identifying the lifetime. So, lifetime will not help here. So, the way we solve the problem, the generic register allocation problem, where the registers are actually spreaded over the hardware, that particular way of identifying the lifetimes, and then finding the conflict graph, and then try to put colors into the conflict graph, and finding the minimum color is equivalent to the minimum number of registers, is not the solution, not the approach to be taken for this particular problem, right. So, here what is more important, identify the access in each step, right. What are the variables are getting access in each time step, and based on their access, you make sure that you map these variables to the register such a way that your access is not getting violated, right. So, that is the problem here, right. So, if I just define the problem statement now. So, this variable to multi-port binding problem can be defined as follows, that given a fixed number of port, maximize the number of variables to be stored in a multi-port memory such that the port limitation is not violated, right. So, I want to map maximum number of variable to a port, to a memory such that their access is getting satisfied by the number of port available. Okay. So, that is what is the problem. So, now you have many n number of variables, right. I want to map those variable to ports. So, I am going to see how many of them can be mapped to memory bank 1, right. And then once that is solved, I can remove those access, because that is done, and then for the rest of one, I again have to try to solve the same problem, how many of them the variables can be mapped to the memory bank 2, and so on. So, this is how I am going to solve the problem. Okay. So, now the question is, I understand the problem and how I am going to solve it. So, what I am going to do here is I am going to give a ILP based solution, integer linear programming based solution for this problem. Okay. And you remember the problem formulation that I have given is solving the it will give you the maximum number of variables that can be mapped to a single register bank. So, as I mentioned, once you get that, you can remove those accesses and you can actually reformulate the problem, and you can actually solve it the same thing again to find out the what are the set of variables can be mapped to register bank 2 and so on. So, basically the whole formulation can be run iteratively to identify the total number of memory bank is needed to store all the variables. Okay. So, this is what is the approach I am going to store, I am going to take, right. So, let us now try to solve the problem. So, what I told you that my objective is to identify the maximum number of variables that can be mapped to a single memory bank which has a fixed number of ports, say a number of ports are there. Okay. So, let us try to formulate the problem. So, I have the Boolean variables bi which is basically for each variables. Okay. So, I have a Boolean variable bi which is basically designate a variable ni. Okay. So, I have n variables, right. Now, what is my objective? I want to so bi equal to 1 if that particular variable vi maps to memory bank. Right. So, I am actually solving for one bank only, how many of the variables can be stored to the memory bank. So, I am not solving the complete problem, I just try to find out the number of variables that can be mapped to a single memory bank. Okay. And if it is 0 otherwise, right. So, I have to find out the maximum variables for which bi equal to 1. So, that is my objective, this is unknown variable. So, what is my objective? Obviously, I want to maximize the number of variable mapped to this particular memory bank. Okay. And what is the constant? It is already known to us that the number of access to this variable should be limited by the number of port available, right. So, I assume that I have a memory bank which has a number of port, right. So, a number of port and then I want to map maximum number of variables such that each time step the number of variable getting access from this particular memory bank is less than equal to a, right. So, how can I write that? So, this bi is basically for the variable if that variable is mapped to this memory bank, and this xi will give the that corresponding operations whether it is getting access in the timestamp or not, right. So, if that particular variable is getting access in the timestamp or not. So, this actually says for each timestamp L the variables that are getting access for that. So, among those register only a number of variables can be mapped to this memory bank. Okay. So, this is the constant. So, the ILP formulation is very simple, that I want to maximize this, that maximum number of variable for those are mapped to this memory bank subject to the access limitation, that every timestamp the number of access to those variable that are mapped to that memory bank should be limited by a, should be less than equal to a. Okay. So, this is what is this constant talks about, and if you give this particular to the ILP solver, what it returns? It will return you the bi value. So, for the variable for which bi is equal to 1, those variable can be mapped to this register bank, right. So, I just solve the problem for one register bank, and then I can iteratively solve these things for register bank 2, memory bank 3 and so on. Okay. So, this is what is the approach. So, let us take an example. Say here the lifetime does not matter, right, but the schedule is very much important, because we need to know what are the operation getting executed in timestamp, because from there only I can understand what are the variable is going to access, right. So, let us say I have given this particular schedule, right. So, in timestamp 1 R3 equal to R1 plus R2 is happening and R12 equal to R1 is happening. Timestamp 2 R5 equal to R3 plus R4 is happening, R7 equal to R3 plus R6 is happening and so on, right. This is how these operations are getting scheduled, right. So, I want to solve this, I want to identify how many of this. So, there are how many variables are there? R1 to R15. There are 15 variables are there, R1 to R15. I want to identify the variables which can be mapped to this register bank, given register bank. Okay. So, obviously, I want to maximize this, that I want to identify maximum number of variables that can be mapped to a particular bank. So, my objective is this, and these are the constants. So, how many constant will be there? I will have a constant for each timestamp. So, how many constant will be there? Since there are 5 timestamp, I will have a 5 constant. Okay. So, what is the constant for timestamp 1? So, I can see here that R3, R1, R2 and R12 is getting access in timestamp 1. Okay. So, that means corresponding variable is B3, B1, B2 and B12. So, and since the number of port available is A, so only a number of these 4 will be access, can be mapped to the same bank. So, that is given by this constant, that B1, B2, B3 plus B4 12, their summation should be less than equal to A. So, suppose A equal to 2, So, that means maximum 2 of them can be mapped to this particular memory bank. Among R3, R1, R2 and R12, only 2 of them can be mapped to this particular register bank if the number of port is 2, right. So, this is for constant timestamp 1. So, similarly, I can identify the constant for timestamp 2. So, I will identify the variable getting access, there are too many. So, I can just note for one more timestamp. So, R5, R3, R4, R7, R3, R6 and R13. You see here this R3 is getting access 3 times, but if I read it once I can use anywhere. So, I do not have to put I do not have to read it 3 times. So, I can consider only R3 equal to 1 time, because it is something if I read it from bank I can use it in multiple operations, right. So, that is why I just put R3 equal to 1 time. So, the corresponding variable is B5, B3, B4, B7, B6, B13. So, what will happen? So, the summation should be less than A. So, that means B3 plus B4 plus B5 plus B6 plus B7 plus B13 should be less than equal to A. So, this makes sure that if A equal to say 2, only 2 of these particular variables among these 6 variables can be mapped to this particular to this memory register bank. So, similarly, I can identify for timestamp 3, timestamp 4 and timestamp 5. Okay. So, these are the constant. So, if I give this to the solver and if I mention this A value, A is a constant, say 1 or 2 or 3, 4, whatever it is, it will tell me the variables that we are going to map to this register bank. You can see understand that there are actually variable which is actually this constant is on, it is not this constant are not independent, right, they are interdependent. For example, you see here B1 occurs here as well as here. So, that means the way I have to assign the value of B1, even B2 also true, right, such that both the constant get satisfied. It is not that I just individually take a constant and satisfy, that will solve the problem, but it is not, because you might put B1 and B2 one bank and then you see and say B1 B2 and say B1 B2, and then you try to such a that and then in maybe in the same next constant you try to map such a way that that particular constant is not getting satisfied, right. For example, you see here this B3 occurs here, B3 occurs here, B3 occurs here. So, the way I am going to assign this B3, if B3 is equal to 1, it will actually impact all these constants. So, the way I am going to assign the value of this 1 or 0 to this B1 or B15, so that all the constants get satisfied, right. That is the ALP will do it for us, right. So, let us say I have one port, okay. So, if I have one port for this, what are the variable maximum, how many variables can be mapped to this, right. So, the solution that will give you this V2, V4 and V8, right. So, basically B2, B4 and B8. So, let us see. So, B2, B4 and B8. I have to make sure that since it is a single port, not any timestamp this a maximum one of them will be accessed, right. So, maximum one of them will access every timestamp. Let us see. So, in timestamp 1 only B1 is getting access, not B4, B8. So, then it is fine. Here B4 is getting access, no B4, B2 or B8. Here B8 is getting access, no B2 or B8. Here B8 is getting access, there is no B2 or B4. Here B2 is getting access, no B8 or B4, right. So, that means this actually this mapping satisfy all the constant, and so if there is a single port, I can map these three variables, that be R2, R4 and R8 to this register bank. Similarly, if say number of port is 2, then it says that you can actually map this V2 to these are the variables. So, let me just check whether that particular mapping is correct or not. So, let me just so V2 V4, V2 V4, V5 V10, V5 V10 and then V12 V14. So, there are 6 registers, 6 variable can be mapped to the same register bank. Okay. And what I have to do, I have to make sure that each timestamp maximum 2 of them is getting access. If not, then this is not satisfying the constant. So, let us see. So, in timestamp 1, I am getting access B2 and only B2, right. So, the and B12, right. So, that means it is getting satisfied that this plus this is greater than or equal to 2 and others are 0. This is 0, this is 1, this is 0, this is 1. So, is get less than or equal to 2, which is getting satisfied. In timestamp 2, I am accessing B4. So, this is 0, B3 is 0, this is 1. I am accessing this one also, B5 is equal to 1, 6 is 0, B7 is 0 and B13 is also 0. You can see only B4 and B5, rest are 0. So, then it is getting satisfied in timestamp 2. In timestamp 3, so I am accessing B5, this is 1, B5, then this is 1, B10 is 1 and this is 0, 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 this is 0. So, I am actually accessing B5 plus B10, which is less than or equal to 2. So, I can understand that this mapping, this 6 variable mapping to the same register bank satisfying timestamp 3 also, and so on. I can show that it is actually satisfying constant 4 and constant 5. Okay. So, this is how the ILP gives me the solution that with 2 bank maximum 6 such variables can be mapped to the same bank. So, once I have this is done, what I just told you that I can rewrite this constant by removing these variables, right. So, I can rewrite this expression by just because this is already mapped, right. So, I can rewrite this expression by B1 plus B3 should be less than or equal to A. So, this is my A1 for the next register bank, right. So, then B3 plus B6 plus B7 plus B13 should be less than or equal to A1 and this is B1 plus B3 plus B7 plus B8 plus B9 plus B11 should be less than or equal to A1, right. So, this is how I can actually rewrite the expression. So, just you can see here that I am removing the variable which is actually 1, because these are the variable already mapped to memory bank 1. So, I have to now solve the problem for the rest of the variables. So, this is how I can actually the value which is 1 I can remove them and the constant will be reduced, and now I want to solve the same problem. So, here I will just put it to 9 because 6 of them is already done. Then I am trying to solve the problem for memory bank 2 and then I will identify the variables which can be mapped to memory bank 2 subject to the number of port, it may be 1, 2 or 3. Okay. So, this is how I am going to solve the problem, and then once the mapping I got it from, then I will remove those variable again from this register constant and I am going to solve it for register bank 3 and so on. This is how I will identify how many register bank is needed and for each bank what are the variables we are going to map. Okay. I hope you understand this, and with this I conclude this today's discussion. Thank you.